Yeah, so thank you, Ravi, for that excellent introduction. So when we think about detecting biosignatures, we often think about, okay, so we're going to disk average that planet, where we're going to get a disk average spectrum. We're going to put that spectrum is going to get analyzed by our telescopes, and we're going to recover that spectrum. It'll have evidence of absorbing molecules. Perhaps it'll have a Rayleigh scattering tail, which will tell us something about atmospheric mass. And those absorption features will fingerprint certain molecules. And we'll use the evidence of those molecules to infer things like the presence of life, oxygen may infer oxygenic photosynthesis, or surface features from the vegetation like Earth, or perhaps other types of pigments we heard about in the previous session. I think we often tend to think of these spectra as sort of out there and static, and the features are there, and maybe we'll have the signal to noise to get them, or maybe they don't. But one complication to think about is the influence of time-dependent properties of the planetary spectrum. So as you're integrating that disk average spectrum, it's going to take a long time. The planet's going to be rotating. It's going to be going through phases. And there are a lot of properties that are going to be dependent on, that are going to change with time, including the surface fractions of different surface types, so surface heterogeneity like land and ocean, cloud heterogeneity, we talked about how important clouds were, and the stochasticity of cloud cover. There are other effects like phase reddening, forward and back scattering from clouds. Your effective path length through the atmosphere will change if you're looking at crescent phase or if you're looking at quadrature or gibbous phase. And those will all affect your signal to noise that you can recover. So this image to the right, this rotating Earth, is actually part of our model that's used to generate the spectral Earth database. Every pixel is a spectrum. And so the blue pixels look like ocean, and then the white pixels look like clouds, and the sort of brown pixels are land surfaces. And all those pixels are integrated together into our disk average spectrum. And we can do this at several different resolutions. And so on the right is the highest resolution, that's number 7. And then number 1 is the lowest resolution. We're adding and summing all these up to get our disk average spectrum. And the more pixels we use, the higher fidelity we can actually represent the spectrum of the Earth. And we can do this for different phases. So for example, here's gibbous, quadrature, and crescent phases. This kind of spans the amount of phases that the range of phases we'll actually be able to observe with direct imaging telescopes because of inner working angle constraints and angular separation between the planet and the star. On the right, you can see here clearly, and thankfully it shows up on this projector, you can see this glint spot. It's very beautiful, but this is really in the model. The model is doing glint. And so what does this look like spectrally? So here's a 1-hour cadence. Earth rotating through a 24-hour period, and I've noted the major absorbing features from water, from oxygen, from ozone, and Rayleigh scattering. And you see a lot of lines there. Those are solar lines that are reflected back. The initial spectrum is at very high resolution, and then we can degrade it to progressively lower resolutions. Now look what happens to the spectrum when I go to crescent phase. Okay, so you can see on the left axis, the spectrum is a lot dimmer, but it's also a different color. It's a lot redder. The Rayleigh scattering tail went away. Relatively, the near infrared is a lot brighter, and the variability is a lot bigger too, because you have a smaller fraction of the Earth. That fraction is covered by ocean or land or clouds that has a bigger temporal impact. Okay, and so we can do this with varying viewing geometries too. So here's a mid-latitude pixel, and you can see Africa and North America then come into view. Equatorial at quadrature, and then pull on. This is the South Pole, and you can see Antarctica kind of peeking out, and then South America and Australia coming in. And so each pixel here, again, is a spectrum. And so how are we doing that? Well, we're doing the full radiative transfer for each individual pixel. That includes absorption, that includes Rayleigh scattering. And we do that for each kind of surface type, each kind of cloud type. And we use line intensities from HITRAN, including the gases that are listed here: water, carbon dioxide, oxygen, ozone, methane, carbon monoxide, and nitrous oxide. So biosignature gases included. And then we use data products from a suite of NASA's Earth-observing satellites. So those data products are publicly available, and they allow us to get things like the mixing ratios of different gases as a function of latitude and longitude. And so this plot represents, for one pixel over the range of data of dates that we've modeled. So this extends a month, as seen from the moon. So Earth is recapitulating all of the phases that you would see as an exoplanet with an edge-on inclination. So this is 1 pixel. This is a range of how these gases vary with time over 1 month. And then on the right, here's all of the pixels of the Earth and all of the times. So what's the full range of the gas at each altitude? And so this is all being self-consistently, this is the real Earth, real retrievals being inputted into the model. And then we can also get the surface coverages. So the ice extent is a NASA data product, so we can get that. And the surface cloud, the cloud coverage extents and positions, we can get that. So when you saw those movies with the clouds in there, those are the real cloud positions for the date and time we modeled, and the real cloud thicknesses. So the left is the clear sky fraction of the different surface types we've modeled. And then the right is the different cloud types. And then this is the observing window we've modeled, and how you oscillate the fraction of each surface type you're viewing because you have one viewing angle. And this is ground truth. So when we're later testing these, we can go back and see what did we put into the model. And so this is a snapshot, 4 snapshot spectra at 4 different phases, at crescent, gibbous, quadrature, and crescent phases. And I've noted up in the full phase panel major absorbing features from different gases. You can see real quick here that as you go to crescent phase, of course, you get a lot less reflected light, and that's expected. Your mid-infrared, of course, is more stable because the night side of the Earth is still warm. It's still emitting light. And so the spectral data products we have extend all of these wavelengths and out from 0.1 to 200 microns. So one thing that's been mentioned is using broadband photometry to try to more encapsulate really quickly what a planet might look like to kind of gauge its habitability before you spend the observing time on spectra. And so we did that too. We did U minus B, B minus V, V minus R, and R minus I magnitudes. Here's how they change with phase. So close to full phase and from quadrature to full phase, you can actually get the modulations from the surface. At crescent phases, you get a lot of phase reddening because you scattered out the blue light. And here's a great color plot that's put together by Jake Lustig-Jaeger. And it shows the range of colors just for the Earth goes through as it goes through its phases. So if we're thinking about surface biosignatures and how they change or how they might be different and how we might identify them, we also have to consider that there's an atmosphere above that planet, and that's going to induce color changes as a function of phase. And so there's going to be a spread in colors depending on when you look at the planet. So you have to consider that. But that spread in color is actually telling you there's an atmosphere, and it's giving you properties about that atmosphere. So we can use that and learn from that. And so I want to talk about other applications of this database. So one thing we did was take a LUVOIR model. So LUVOIR is a large UV ultraviolet optical infrared telescope concept. And so we used a coronagraph noise model from Tyler Robinson, and we simulated, OK, what would LUVOIR see at these different phases using as input our spectral Earth database. And so here you can see you've got a great Rayleigh tail, O2A band, ozone band, Hartley-Huggins UV band, Chapuis ozone band. And let's look at them as they change through phases. So if you look at a gibbous phase, our error bars have shrunk a little bit. I should say that the parameters we assumed for this were a spectral resolving power of 80, mere diameter of 12 meters, and distance of 5 parsecs. And this is for a 100-hour integration. So 100-hour integration gives you these error bars with the 12-meter telescope. Now, if we go to crescent phase, you can see a big difference. We've completely removed the Rayleigh scattering tail, so that's gone. The Earth is now a different color than it was before. But another cool thing that happens is that the Chapuis ozone band now gets deeper because your path length through the atmosphere is bigger, and so you get more ozone absorption. Now that U-shape in Earth spectrum is actually really diagnostic of Earth spectrum, and separates it from the other terrestrial planets and from potential abiotic planets we could imagine, just like bare rock with a nitrogen surface would be blue, and it wouldn't have methane absorption that would separate it out from Neptune and Uranus. But it wouldn't have that U-shape. And there it is again. And so the idea here is that you could get broadband photometry to look for that U-shape before you invested in the spectrum. Surface mapping is something that's been talked about. I want to advertise a poster by Jacob Lustig-Jaeger, who's going to give a talk in this room at 2:15 on Wednesday, using the spectral Earth database I've mentioned to test retrieval models and see how well we can actually pull out ocean fraction, vegetation fraction, and land fraction. So please come see that. One other thing that's kind of cool is that this model has also been used to model the Earthshine effect on permanently shadowed crater regions on the moon. So it's permanently shadowed from the sun, but not from the Earth. And so our model's been used for that, a little bit beyond biosignatures, but it shows the kind of flexibility of what this database can be used for. And so finally, I would kind of want to ask people in this room who might be working on instrument simulators, who may be working on different kinds of biosignatures, what can the spectral Earth database do for you? We can do arbitrary phase viewing angles, phase and viewing angles. We can do different observing cadence, so an hour, 15 minutes. We can work with that, and we can switch from one surface to another. So we can switch out our vegetation for anoxygenic phototropes, for example, and look at the effect on the spectrum and how recoverable with retrieval models that biosignature would be. And so with that, I'll thank you all and take questions.
Thank you, Eddie. So that was a really great talk, not because you're a session chair, but it's really good. So, all right, we are open for questions.
Thank you, Eddie. Great talk. So a lot of the planets that we're most interested in at the moment regarding recent discoveries are planets around M dwarfs, where the integration time will be a non-negligible amount of the orbital period.
Yes.
So in that case, I guess you have a convolution of many of these specific phases you've been shown. Is that going to be a problem for backing out individual spectra corresponding to a specific phase in those cases?
Yeah, so that's a great question. And to answer that, two things. One is the angular separation of the planet and star is very bad for M stars. You know, the habitable zone is close by, so we'll only be able to directly image the close by ones, but we still might be able to do a few. And to answer your question is, absolutely, you would have to consider the fact that the planet's changing in phase, depending on your inclination. You might be lucky if it's face on, it's always quadrature. And you have to consider that, you have to consider its rotation. And so to back it out, to back out those quantities, you would need more observations. And in terms of the specifics of the retrieval, I would encourage you to come and to Jake's talk on Wednesday. But I would say that in terms of rotation, I don't think that it's going to be any worse for rotation because you're still going to have to look at the planet for the same amount of time, whether it's an M star or a G star. For disentangling those phase effects, maybe that's worse. But what you can do is you can bin. So you can say, well, I looked at it for this amount of time in this phase, and if you've observed over several orbital periods, you can rebin your data, depending on how you do the integration, and you can do the same thing you do with Earth orbiting a G star.
Great, thanks.
Sean, good.
Hey, Sean.
Hey, Eddie. Great talk. That was at Crescent Phase was particularly cool. So the question I have is thinking on the other end from the color spectrum,
Yes.
One thing that the LUVOIR STDT has been telling us is that we need to think of a way to fingerprint these different planets because we're going to observe them for, let's say, 100 hours, go away to other science or maybe other exoplanet targets, and then come back, and they'll all have moved in their orbits.
Yeah.
And one thing we're worried about is this phase dependence
Right.
blocking us from knowing which planets are the ones we saw before versus something that's just popped outside the IWA.
Right.
Can you guys look at something like, the spectral resolution we have to get at to find the fingerprint, to find the things that aren't dependent on phase, or maybe, I don't know, just thoughts.
Well, I mean, it depends if you're investing a lot of time with the planet and you get the rotation rate and you can match rotation rates.
Yeah.
But again, that takes a long time. And it depends on how you do your integrations. I think when you talk about a 100-hour integration, really what you're talking about is like 100 one-hour integrations or something like that.
Yeah.
1,000 10-minute integrations. Or I did that wrong, but
well,
you know what I mean.
The detector array at some cadence. Yeah.
But then you can rebin those data, and then you can get a better time-dependent information from that.
So maybe temporal. The signature may be in the temporal domain, not the spectral domain, is what you're suggesting.
Yeah, so yes,
Okay,
that the temporal domain is another leverage point for
Yeah.
this, yes.
Okay, awesome, thank you.
All right. So we are done for this session, the morning session, and we'll meet again at 1:30. Thank you.